Welcome to The Explainer. Today, we're diving into what is, without a doubt, the biggest headache in all of physics. It's a problem that comes from a simple but frankly terrifying fact. Our two most successful theories of reality, general relativity and quantum mechanics, completely and utterly contradict each other.
And look, we're not talking about some small technical disagreement here. This is a full-blown civil war at the heart of modern physics. It's a deep, fundamental clash about the very nature of reality itself, and it's a puzzle that has kept the smartest people on the planet up at night for almost 100 years.
So you've got these two titans, right? In one corner, you have Einstein's masterpiece, general relativity. It's just beautiful. It paints this picture of a smooth, sweeping cosmos of stars and galaxies all waltzing together on this dynamic, curving fabric of spacetime. And then in the other corner, you have the weird, wild world of quantum mechanics. It governs the subatomic realm with mind-boggling accuracy. The problem? They describe our universe in ways that are just fundamentally incompatible.
So naturally, physicists thought, hey, let's just mash them together. Let's build a quantum theory of gravity. Sounds simple enough, right? Well, when they tried, they ran into something deeply unsettling. A consequence that points to a universe where the clock just stops, where time itself completely vanishes from the picture.
Okay, let's get into the nitty-gritty. At the very center of this whole mess is one single, deceptively simple equation. It's the result of that very first serious attempt to merge the two theories, and honestly, its implications are just staggering.
This is it, the Wheeler-DeWitt equation, and its stark simplicity is really deceiving. What it basically says is that if you take the total energy of the entire universe, the Hamiltonian, if you want the technical term, and you apply it to the wave function of that universe, you get zero, always.
So what? Why does zero matter? Well, in physics, energy and time are deeply linked. If there's no change in energy, it means there's no evolution. Nothing happens. That's why they call it the problem of time, or the frozen formalism. It literally describes a static universe. No change, no before, no after. It means our entire experience of time flowing by might just be a grand illusion.
Okay, so if the universe is frozen, how do we get out of this mess? Well, that's the billion-dollar question, isn't it? For decades, some of the most brilliant people alive have been cooking up all sorts of incredible theories to try and bridge this chasm and get the cosmic clock ticking again. Let's do a quick tour of the main contenders.
All right, first up is the original approach, canonical quantum gravity. The thinking here was pretty straightforward, Let's just take the standard recipe for quantum mechanics and apply it directly to Einstein's theory of gravity. But this is the very approach that gave us the frozen universe problem in the first place.
Now, to be fair, it did get one really big thing right. It was background independent. That's a fancy way of saying it didn't need a pre-existing stage for reality to play out on. Space-time itself was part of the show. That's a huge deal for relativity. But the price it paid was steep, a universe where, mathematically, nothing could ever happen.
So that first path kind of led to a dead end. The next group of physicists decided to try something totally different. Instead of quantizing gravity, what if we build space itself out of quantum bits? This is the core idea of loop quantum gravity. It says space isn't a smooth sheet. It's more like a fabric woven from tiny, discrete loops. You could almost think of them as atoms of space.
And this idea had some incredible successes. For one thing, it gets rid of the singularity at the Big Bang. Instead of an infinitely dense point, you get a big bounce. Super cool, right? But it couldn't shake the problem of time. It basically just inherited it. The only workaround was to kind of cheat. You just pick something in the universe that's changing and say, okay, that's the clock now. The problem is, any choice feels totally arbitrary.
Okay, so Team Loop Quantum Gravity was still wrestling with this time problem. Meanwhile, another camp went in a completely different direction. They said, forget points, forget loops, what if the universe is made of music? That's the heart of string theory. The idea is that every single particle is just a tiny one-dimensional string vibrating at a different frequency, like a note on a cosmic guitar.
And mathematically, string theory is gorgeous. It's incredibly elegant. Gravity just pops right out of the math. No extra work needed. And best of all, no problem of time. But, and this is a huge but, it only works if you assume the strings are vibrating on a fixed, static background. It needs a stage to perform on. And that completely violates background independence, the very principle from relativity that started this whole mess. So it solves the problem by, by ignoring it.
So where does that leave us? After all this brilliant work, we're still stuck at a philosophical crossroads. We have these amazing theories, but there is absolutely no consensus on what time even is. Each approach is placing a completely different bet on the fundamental nature of reality.
In one view, time is frozen, a stubborn illusion that doesn't exist at the deepest level.
In another, time is chosen. You have to arbitrarily pick something to act as your clock just to make the math work.
And in the most popular theory, time is simply assumed. It's just part of the furniture of the universe, and we don't ask where it came from.
Frozen, chosen, we're assumed. I mean, it kind of feels like we're out of options, right? You might think the whole quest is doomed. But what if there's a fourth option? What if time isn't any of those things? What if it emerges from something deeper?
There's a relatively new idea on the block. It has a bit of a mouthful for a name, the Conformal Emergent Reality Model, or CERM for short, and it proposes that maybe, just maybe, we've been asking the wrong question all along. It suggests that both time and space aren't the fundamental building blocks we thought they were.
This theory claims to finally resolve the central conflict. The idea is that time emerges directly from the changing shape of the universe itself. Think about it like this. The very curvature of space-time, the thing that is gravity, also acts as the master clock. The universe's own evolution creates its own timekeeper. The clock starts ticking all by itself, with no freezing, no choosing, and no assuming.
Now, the details of how this works are, well, that's a whole other explainer. We will definitely dive into that soon. But for now, it leaves us with this really mind-bending question to chew on. What if the time we experience every single moment is just a shadow, an emergent property of a deeper, timeless geometric reality? I mean, what would that even mean for our understanding of, well, everything?